the next video lecture on the retaining wall in continuation with the previous one. In the previous lectures we had an idea about the retaining wall, its various types, and the different cases of earth pressures that may act on the retaining wall. Now we will begin with the design of RCC cantilever retaining wall. So as explained in the previous lecture, a cantilever retaining wall is the one which is having a stem, a toe slab and a heel slab supporting the backfill. These are the various versions of cantilever retaining wall which we can have. You can note here that this another element is shown here, which is the key or shear key. I will explain its role later on. It is provided in some cases of cantilever retaining walls. So all these three elements behaves like cantilevers supported at this particular portion. This stem behaves like a cantilever fixed at this portion and free at this. Heel slab also behaves like a cantilever, free here, fixed here. Toe slab, free here, fixed here. So before beginning further, we will have an idea about the different forces acting on cantilever retaining wall. So consider a retaining wall, cantilever retaining wall having a stem, toe slab and heel slab supporting this backfill. So there are different types of forces that act on it together. First is the lateral force due to active earth pressure PA, shown here. This will act like this at a distance of h/3 from the base of the retaining wall. Next is the weight of earth supported on heel slab W1. The weight of the backfill which is supported on earth which is supported on the heel slab will give a force equal to W1, then W2 which is the weight of stem, W3 which is the weight of base slab, W4 which is the weight of earth on the toe slab. Here as you can see on the toe slab also some of the earth is resting, so it will also put a pressure or weight on the toe slab, but as it will be quite less as compared to this, therefore it may be neglected. Then there is another force which is the passive earth pressure force acting here. Due to the presence of this backfill, there will be another force PP which will act in this direction towards the retaining wall. So these are all the types of different forces acting on the retaining wall. Now we continue with the next very most important part of retaining wall, that is stability or the failure conditions of retaining wall. As I have told many times, before designing any type of RCC or any other material structural element, we must first know its behavior, structural behavior, and the modes in which it can or it may fail. For example, when we designed beams can fail due to bending. So whenever we designed beams, the bending moment was considered as the primary action. Similarly, when we design columns, the axial compressive force or it can fail due to the axial crushing. So the axial compressive force was the basic force which we used for analyzing or designing the columns. So similarly in this case also, before designing the retaining walls, similarly when we designed footings, we considered the various criteria in which the footings can fail, for example by one-way shear, by two-way shear or by bending. So as here also we will first have a look on how the retaining wall can fail so that we can provide options to recover these failure or prevent these failure or to make the retaining wall stable. So these are the three main types of failure modes of a retaining wall: overturning, sliding and failure of undersoil, as you can see here and here also. Overturning, as you can see, which is a very common phenomena, due to this earth pressure the retaining wall can easily topple like this. It can easily rotate or topple like this. Lateral pressure, the wall can slide in this particular direction. This is the original retaining wall and it can slide to this position due to the lateral earth pressure. The third type of failure condition can be if the soil beneath the retaining wall fails in any way. Normally the soil fails when its bearing capacity is less than the pressure acting on the soil. So these are the three cases of failure of retaining wall. Retaining wall may fail in either of these three ways. So our motive is to prevent all these types of failures. A perfect retaining wall will not encounter these type of failures. So once we know about these failure conditions or stability conditions, we can keep these in mind while designing and designing the different parameters of the retaining wall. So we will look at these one by one. So first is overturning. So overturning is very common type of failure due to this earth force. This point is free and this is fixed, hence it can easily topple if the retaining wall is not designed properly. This will happen when the overturning moment, this is the overturning moment due to these force, is more than the restoring moment. As you have previously studied in all design subjects and in structural analysis also, there are two types of forces in any structural element. First is the action and second is the reaction. Action is the one which creates failure and reaction is which prevents and which provides resistance to that particular action. So similarly here, for this overturning we will need another moment in the opposite direction which will prevent the overturning from happening. So some of the components of retaining wall will lead to overturning and some of the component will lead to restoring or resisting. So it is very clear that of course this value should dominate this value so as our retaining wall remains stable. So the restoring moments should be always greater than the overturning moments. I will explain it in detail here. So look at both these diagrams. First we look at this particular diagram. Here we have a cantilever retaining wall acted upon by earth pressure PA. So as it is clear, due to this PA force, some moment will act which will lead to its toppling or overturning. So let us consider a point here at the base of toe slab. This is the toe slab. If we consider any point here or either here, you can take any point. This is the force and this is the point. When we take the moment of this force about this point, that moment will have this direction like this. So this moment will cause the overturning, hence I will denote it as M0. Similarly, we can see other forces also acting on the retaining wall. I have explained all these to you before. This is the weight of backfill, which is the force acting vertically downwards. So what is the behavior of this force? This is the force, this is the point. If we calculate the moment will be like this. So as you can clearly see, this is counterclockwise and this is clockwise. This is counteracting this particular moment. So this will be the restoring moment. Similarly, weight of stem will have this restoring moment, weight of slab will have this restoring moment, and here this is the passive earth pressure which I explained earlier. Passive earth pressure will also have this moment. So these all are opposite to the overturning moments and we call it as the restoring or the resisting moments. So here MR should dominate M naught. MR should be greater than or equal to, greater than M naught. Another case that is of inclined backfill. Note here that this was for horizontal backfill. As this is horizontal, then the lateral force is also horizontal, contributing to overturning moment. Here this is the inclined backfill, hence there will be inclined force. So if we divide these inclined force into its two components, that is horizontal and vertical components, so I ignore the inclined force and I just bring the horizontal and vertical components of that inclined force. So as it might have been clear to you by now that as the direction of loads is different, the main action of overturning will also be different. So let us look at PH, horizontal component. The horizontal component moment, the moment of horizontal component at this point will be like this. So this will be overturning M naught. And for vertical, this is the vertical force and this is the point. So look at my cursor. So this will be like this. This will be like this. This is restoring moment. So keep it in mind that whenever we have inclined backfill, it will have two individual components and both will contribute separately and differently to the retaining wall stability. So let us go again to our presentation. So as explained here, the overturning moment must always exceed, the overturning will happen when the overturning moment exceeds restoring moment. So in order to have stability, the restoring moments should always be more than the overturning moment. So these are the overturning moments and these are the restoring moments. Then restoring moments should always dominate the overturning moment for stability. Overturning moments are due to the passive active earth force, and the restoring moments are due to the weight of backfill, weight of the wall and lateral earth pressure. And in case of inclined backfill, the vertical component of the inclined force will also contribute to restoring. I have already explained it to you. So it is now very clear to you that in order to have stability against overturning, our MR should always be greater than or equal to M naught. So IS 456 has defined a specific value that for how much times the MR should be greater than M naught. MR should be greater than M naught, but there should be quite a gap between both these. So according to IS 456, MR should be 1.4 times more than M naught. Only MR greater than M naught will not do. There should be a variable difference between both these values. So if I rearrange it, so MR upon M naught should be greater than equal to 1.4, and this 1.4 is known as the factor of safety against overturning. So keep it in mind always that the factor of safety against overturning is 1.4. So this is the equation. Factor of safety is restoring moment upon overturning moment, and its value should be always greater than equal to 1.4. If you see clearly, in this equation we have another value written here, that is 0.9. Factor of safety is restoring moment upon overturning moment. Then why this 0.9 factor here, 0.9 into the restoring moment is written here? So this is a very important and deep meaning. So for this we have to recall back your concepts of load factors. In the previous design numericals, like in beams and columns and slabs, when we take the live load or dead load, we always increase our load. For example, if you have a value of load L, then we always take it as 1.5 L. This is because in future the load may increase than the actual assumed value, so we from the beginning we take it as a larger value for safety or over safety, to look at the worst case scenario. So this was the case which we used to take later. So here this 0.9 is also a load factor, but note here that 1.5 is a value greater than 1, that means we are increasing the value of load, and here this value is 0.9, that is we are decreasing the value of load. If actual value is L, by multiplying it by 0.9 we are reducing it. So why we are doing it, it is very important. As you know, restoring moment is good for your retaining wall, and it should be more and more. So in case the loads increase in future, that is, for example, we learned earlier that weight of soil is contributing to the restoring moment. So if in future the load increases, then the restoring moment will also increase, and if the restoring moment will increase, it will counteract the overturning moment more and more, so it will be good for the retaining wall. But while we are designing, we should not look for the positive part, we should always look at the worst case scenario. So what is bad for our retaining wall? If this load by any chance, unfortunately, this soil load or any of the restoring force decreases in future. So what will happen if the weight of soil or any restoring force like the weight of wall, etc., if it decreases in future, then the restoring moment will also decrease, and if the restoring moment will decrease, it will ultimately it will not counteract overturning moment much. So this is the worst case scenario for your retaining wall. Hence the worst case scenario of retaining wall is when the restoring forces are getting reduced. So for safety, from the beginning we presume that the loads may reduce, hence we put a load factor of 0.9. I hope it is very clear to you. You can refer to your previous books and previous concepts of load factors for better understanding. So 0.9 factor is here provided to account for the variability of load, that is decreasing of load in future of the restoring force. So this expression will change to this if we take this 0.9 here. So 1.54 divided by 0.9 will lead to 1.55. So the factor of safety against overturning is 1.4 or 1.55. But 1.4, if you are taking 1.4, then always remember to multiply here by 0.9. Okay, so this is the factor of safety against overturning. So I have explained it. You can see this slide again for better understanding. WS restoring force, WB restoring force, WL restoring force, HP, this is also restoring force, WE also restoring force, WX also restoring forces, and this force HA and H1, I don't know what it is written, H1, these are the overturning forces. So this factor of safety has already been explained. So if we simplify this formula, the factor of safety against overturning will be restoring moments. What are the restoring moments? Passive earth pressure and the different weights acting here, as I have circled here. So the passive earth pressure, the moment due to the passive earth pressure at this point will be PP into H by 3. Okay, so if this is a triangle, this is PP. We are calculating the moment at this point, so the moment will be PP into H by 3, and the other restoring forces are all the weights, WS, WL, WW, WX, W0, all these forces are the restoring forces. So the moments due to these forces will be WA into its distance, perpendicular distance from the point where we are calculating the moment. So for this case, if this is the weight of soil, the moment due to this weight of soil at this particular point will be Ws into this distance x1. Similarly for Ww, this will be x2. So we have just written here that summation of W into x bar. So these all contribute to the the restoring moments, divided by the overturning moment. Overturning moment is only one, that is PA into h by 3. So this is PA. The moment of this force about this point will be PA into the vertical perpendicular distance, which is h by 3. If in this case we have inclined backfill, then this particular equation will change a bit. Here we will have another value, that is the the vertical component of the inclined force will contribute to restoring, and in case of PA we will have PAH, that is the horizontal component only. This I have explained in detail before. So I hope the overturning concept is clear to you. So if in any case you are given a problem that you have a retaining wall near your surrounding, or if you are given with any retaining wall with given dimensions and soil properties, and you have to check its stability, so what you will do, you will calculate all these forces which are shown here, like WL, WW, WS, etc., and then you will calculate the restoring moments due to those forces and combine those, and all the overturning moments, combine those, and then you will calculate the factor of safety. So if that factor of safety is greater than or equal to 1.55, then your design is safe and your retaining wall is safe against overturning. And if it in any case it comes out to be less than 1.55, then there is some problem with the retaining wall, so you will have to redesign it. So this is all about the overturning. Next type of failure is sliding, which is very clearly visible to you from this particular diagram. Due to the lateral active earth pressure acting in this direction, there are high chances that the retaining wall may also slide in this direction like this. So what you will do here, we have to prevent this sliding. So as I stated earlier also, this is an action and you will have to provide, or there is already an inherent reaction against this. So the retaining wall will slide when in lateral direction due to lateral active earth pressure. Okay, sorry, there is some grammatical mistake here. The retaining wall will slide due to the lateral earth pressure. Sliding will occur when the sliding force is greater than the frictional force. Sliding force here is the lateral active earth pressure, that is which moves in this direction, and the frictional force is opposite to it, which is in this direction. So sliding will occur when this dominates this. So we have to prevent this from dominating this. This frictional force must always be greater than the sliding force. So I will explain it to you in detail. Now look at the similar diagrams as I have shown you earlier. This is a retaining wall. This horizontal backfill has horizontal earth pressure force like this. This will tend to slide the retaining wall in this direction like this. So as you must have seen in your basic classes of physics, you must have studied, whenever such kind of force is acting, another force always acts, either in any structure or in any type of material in this universe. So what is this type of force? This is the frictional force. The sliding force is always opposed by the frictional force. And what is the frictional force? Frictional force is a function of the vertical forces acting on the object, and it depends on this value, that is the coefficient of friction. This you all must have studied in your basic school classes of physics. Mu is the coefficient of friction which depends on the two surfaces. That what is the coefficient of friction between two forces. Higher the coefficient of friction, higher will be the frictional force. So as it is evident, the frictional force here must always be greater than the earth pressure here. So how will we calculate the frictional forces? Mu is the coefficient of friction between the soil present here and the surface of this retaining wall, which we will have to assume, or which will be given. It depends on the angle of friction between these two, and mu is equal to tan delta. This is all basics physics, you need to recall it. So what is V here? V are all the vertical forces, that is V, weight of the retaining wall, weight of stem, weight of base slab, and this is weight of backfill. I have not shown it here, but this is weight of backfill. So what you will do, you will combine all the vertical forces and multiply it with the coefficient of friction. You will get the frictional force. There is another frictional force acting here, which is actually not frictional force. I should not call it frictional. It is basically the reactive force against the sliding force, which is the passive earth pressure, which is clearly in the opposite side as PA. But as we are already ignoring it earlier, we can or cannot ignore it here also. So the sliding force is this, and the forces due to contributing to frictional forces are all the vertical forces and the passive earth pressure. Similarly for inclined backfill, but we will have the PH, that is the horizontal component, will be the sliding force, and PV will contribute to the frictional force. So this PV will be added to all these vertical forces to get the frictional force, total frictional force. Now let us go back to the slides. So sliding force is due to lateral active earth pressure, and frictional force is due to the passive earth force, and it is the function of weight of backfill, surcharge, and weight of retaining wall. F frictional is mu times. Mu is the coefficient of friction between the soil present here and the base of your retaining wall, which depends on the friction angle between the slope of the soil. So this diagram here shows the different sliding forces and frictional forces. This is the sliding force, and this and this, all these contribute to the friction forces. So as it is clear, must be clear to you that the frictional force should always be greater than the sliding force for the stability of against sliding, and the frictional force should not be less than 1.4 times the sliding force. As in the case of overturning, IS code has here again fixed the value 1.4, that the frictional force or reaction force, which frictional force can also be known as the restoring force. Restoring force should be greater than or equal to your sliding force, and this value should be 1.4 times greater than the sliding force. So here the 1.4 is the factor of safety against sliding. Similarly, as in the previous case, we have multiplied it by a load factor of 0.9. I have explained already the reason why 1.9 is being taken. So restoring forces are mu into summation plus here PP, if you are not ignoring the passive earth pressure. Mu is the coefficient of friction, and summation W are all the vertical downward forces acting on the retaining wall. PAH is the horizontal earth pressure acting on the retaining wall. So I hope sliding is clear to you. If the factor of safety comes out to be less than 1.4, that is if the retaining wall fails for sliding due to some reason, then there is a solution which we can implement in the retaining wall. a shear key is provided. I have already in the previous earlier slides I have mentioned shear key. What is the basic purpose of shear key? I think it will be clear to you. Shear key is an additional part protruded from below the slab like this, which is extended. Basically the retaining wall is extended downwards up to a particular height. The basic purpose of this this particular portion shear key is that this is provided to increase the restoring force. It is common sense that if we increase this particular portion like this, actually originally this passive earth pressure was only at this point, this particular height. If we extend our wall here, then it will also extend this much area we are extra area we are providing, so that the extra restoring forces and can act which can counteract the sliding force. So I hope the concept of shear key is clear to you. Shear key is provided when the factor of safety of sliding comes out to be less than 1.4. so to increase the value of restoring force, we provide another structural element here so that the factor of safety comes out to be greater than 1.4 or 1.55. So this is the sliding stability against sliding of retaining wall. Now the last type of failure which can happen in retaining wall is the failure of undersoil, which is below the retaining wall, and it depends on the bearing capacity Q of the retaining of the soil underneath the retaining wall. As you have studied earlier also, the pressure acting on the soil should always be less than its bearing capacity. So soil underneath retaining wall may fail if the soil pressure exceeds the bearing capacity of soil. So this is the soil pressure diagram acting below the retaining wall. P maximum should be less than the safe bearing capacity of soil, and P minimum should not be negative. So if you satisfy both these checks, if your retaining wall satisfies these checks, then there will be no failure of the undersoil. Here P maximum and P minimum are the maximum and minimum soil pressures acting at heel slab and at toe slab and at heel slab. So the expressions for these are these two, where W summation is the weight of all the forces acting on the retaining wall, and B is the width of the base slab, this, and E is the eccentricity of the resultant load, which is given by this formula B by 2 minus X bar, where X bar is MR minus M naught. MR is the restoring moment, M naught overturning moment, and summation W is the summation of all vertical downward forces. So you calculate P max and P minimum and check, apply both these checks. If both these checks are correct, then your retaining wall will not fail, then there will be no failure of the undersoil. Alternatively, you can calculate another check or apply another check, either this one or the next one which I am explaining. The next check is that the resultant load must fall in the middle third zone, or in other words, the value of E, which we have calculated like here, E is B minus 2 minus X bar. The value of E the location of E must be in the middle third portion of the base slab of retaining wall, if like this. So if E lies outside of the middle third zone, then there can be a failure of undersoil. So if you apply this check or you apply this check, both are almost same, so you can use either of these checks to check the stability of the undersoil. So now we are done with the stability. Now we will look at, we need to know the behavior of your structural behavior of your retaining wall, cantilever retaining wall. As I have explained earlier to you, there are 3 cantilevers in retaining wall. First cantilever is the stem, second is the heel slab, and third is the toe slab. The stem is like this, the fixed end is here and the free end is here. So we will look at the individual components. To study the cantilever action, we must know the direction of load, which is very important. So for the stem, which is the most prominent force acting on the stem, which will lead to the cantilever action, that is the earth pressure, PA. So this is your stem and this is your earth pressure. So your cantilever, as you know the concept of cantilever, if a load is from this direction and this is fixed at this end, the cantilever will behave like this. So this can bend like this. So now this will be the tension zone and this will be the compression zone for stem. Now we look at the base slab. First, heel slab. Heel slab is the one which is fixed at this end. I will make this separately here. This is your heel slab. So what are the different primary forces acting on the heel slab? First is the weight of backfill from above, and second is the soil pressure from below. So according to you, what should be the more bigger value of these two? This is the downward force, this is the upward force. The net resultant force must be the subtraction of both these forces. So as this is a larger backfill here, so the value of this force will be large as compared to the soil pressure from below. So the net value of load will be downward here. So we have a heel slab with vertical downward load. So as we know the cantilever action, this will behave like this. So the tension zone is upper zone and the compression zone is the below zone. Now we look at the toe slab region. In toe slab, it is the exact opposite of heel slab. In the heel slab we have the weight of backfill from above and the soil pressure from below. As I have repeated many times, this depth is quite less, hence the value of this backfill will also be less. So the net force will be upward. This value will always be more than this value, so the net direction of load will be upward. So in case of toe slab, this is a toe slab, the net force is upward, hence the cantilever action will be like this. So this is the tension zone and this is the compression zone. So I think it is clear to you now that how the individual cantilevers are behaving. Now let me refresh with this slide. So this is the tension zone here, this is the tension zone here, and this is the tension zone here. So as you know from RCC1, the reinforcement is provided along the tension zone. So in stem, the main reinforcement will come along the inner edge, in the heel slab along the top edge, and in the toe slab along the bottom edge. So this will be the basic reinforcement location for the cantilevers of the cantilever retaining wall. So I hope the structural behavior and different forces acting on cantilever retaining wall is clear to you. Now in the next video lecture I will continue with the design of cantilever retaining wall with steps and with numerical.